Hello everyone, so welcome to class 4. So today we'll look at, we'll try to finish off the tensor algebra elements that we intend to do in this course. And so in the last class we were actually trying to look at what these, what really properties as tensor mean with the example of one of these second rank tensors, which is conductivity. We said electric field applied does not need to be in the same direction as the current measured. We took the example of so in general so that is the case in all the materials that we have studied, silicon, germanium, all these are nice isotropic cubic materials. Actually if you do not understand what isotropic and cubic means, that is okay, because in the next module of this course we are actually going to do that, see what these materials, what these terms actually mean. But so we did not have to bother if we were measuring on these sort of standard materials, we did not have to bother that so they have cross components, they have cross diagonal elements in their conductivity tensor. Now that would yield such effects where I can have electric field in one direction and I can generate current in the other direction, or vice versa, I can have current in the first direction and I can generate electric field in another direction, right. Now this is the so called Hall effect, right. So I mean, so even on isotropic materials we have studied such an experiment, or if we did not, you can go and do some self study and try to understand what Hall effect is, where you apply current in a certain direction and you measure electric field in another direction. And so there is some sort of cross coupling between current in this direction and electric field in this direction, and this cross coupling in isotropic materials is made feasible, made possible because of the existence of a magnetic field. Magnetic field tries to force the carriers in to bend, and then applies a force in that direction, and hence that force converts into an electric field. Okay. Now that is all right in isotropic materials. I told you how very simply what people do to measure Hall effect. So they apply a magnetic field, one value of magnetic field with some standard magnets, and then they measure so this J2 by E1 sort of quantity, or E2 by J1 sort of quantity as a function at that particular magnetic field, and estimate the Hall resistance. However, this will yield problems if your material to start with is not a good material like silicon or germanium. Rather it is something like gallium oxide, where to start with itself you have some transverse components of the sigma 1 2 sort of component. Okay. So that is where we ended in the last class. So it is not surprising that materials have sigma 1 2. So not all materials need to be as symmetric as silicon or germanium, right. So materials can have cross components of conductivity, that is perfectly all right. Okay. So we will take off from there, and we will look at some more mathematics. And in fact 2 classes ago I said I will define a tensor. I have not yet come to the stage where I can define a tensor, but today probably we'll do that. So speaking about second rank tensors, so we have Ji, which is the current density in the ith direction, is equal to sigma ij Ej, right. So so this is how Ohm's law is typically written. So I apply electric field in the jth direction and I have current in the ith direction, right. So this sigma ij typically is a so it can be a tensor which has all possible components, sigma 1 2, sigma 1 3, sigma 1 2, sigma 1 3 again. It is a symmetric tensor. The reason why this is symmetric will become clear later on. Sigma 2 2, sigma 3 3, sigma 2 3, and sigma 2 3. Okay. However, so the sort of materials that we studied about, right. So in Hall effect in the previous class we said that okay, so there are these anisotropic materials that one needs to be wary about, which has these cross components of sigmas. But the typical materials that we study about, sigma is just equal to sigma 1 1, sigma 1 1, sigma 1 1, 0 0 0 0 0 0 in nice materials such as silicon, for example, or germanium or diamond, and so on and so forth, right. So this second rank tensor is an isotropic tensor. It is the same in all sorts of directions. Okay. Now if I look at rho, which is the resistance or resistivity, rho, so typically how so rho is just written as or sigma is just written as rho inverse, right.
So if I have an isotropic tensor, then rho will just be 1 by sigma 1 1 1 by sigma 1 1 1 by sigma 1 1, right? So one may argue that here, for example, if I have to measure sigma, I have to apply, so for measuring sigma, one needs to apply electric field and measure the current, right? Whereas for measuring rho, right, so rho will then turn out to be, Ej equal to rho Ji, or it's the inverse rho Ji Ji, right? So something like this will be rho, and so here my cause is current and effect is electric field, right? So the measurement, ideally, if I have to measure rho, I have to apply current and measure electric field, but if I have to measure sigma, I have to apply electric field and measure current. Now you may say, what is the difference, right? In a linear material, right, so where current versus voltage is just very straight, it doesn't matter, right? So it's the slope of this current versus voltage gives me sigma or rho, okay? Whereas in a non-linear material, right, so in a non-linear material where sigma is changing somewhat like this, right, so there these things matter, right? So for example, I give you the example of what is called a memristor, right? A volatile memory, right? So these devices look something like this, right? So if I apply voltage, right, so the device so initially conducts very low current, suddenly the current increases, and then this goes from a low resistance state to a high resistance state to a low resistance state. And then once I'm coming back, right, so this is this is V, this is I. So once I increase the voltage, this is the trajectory. Once I decrease the voltage, this is the trajectory, right? So there is some hysteresis here. So at this voltage, if I fix this voltage, some sort of a voltage V1, at V1, I have two solutions for current, actually three solutions. Right? So there are this I1 and I2 are stable solutions. I1 and I2 are stable for this device. And there is another current which will be in between, let's call it I3, will be unstable solution. Right? Now if I'm controlling current, if I'm controlling voltage, I just see stable solutions depending on whether I am increasing the voltage or decreasing the voltage. I see either I1 or I2 as a solution. Okay, but if I control current, then I see something like this. So at a given current, however, there is only one solution for voltage, right? So at this current, there is only one solution for voltage, right? So although this seems to be an unstable solution when I apply voltage, this becomes a stable solution when I apply current. Right? So as a result, if I just take the slope of this and say slope gives me resistance or conductance, right? That is in this current controlled experiment, in a current controlled experiment, right? So I have to look at what dV by di is, and that gives me what is called resistance or differential resistance. Whereas, in case of, so if I want to really measure the conductance, right, so these two curves are different. This is measuring the conductance of the device. Conductance measured, and this is measuring the resistance of the device, right? So in such nonlinear devices, so this is, let me box it with with red and say resistance is measured. So in a nonlinear device such as this, right? So in a nonlinear hysteretic device, resistance and conductance need to be measured separately. The experiment to do that is separate. R and conductance, let's call it as capital S, or rho and sigma need to be measured. Okay, so let me erase this. Need to be with different experiments. Okay. Okay. So that's a small digression, but having said that, so let us now look at some of these tensor properties. So we said, again, let's go back to a general form of writing these second rank tensors. Let us start with second rank tensors, right. So I said Pi is my effect vector, and effect vector is given as my response function, which is Tij, which is a tensor, a second rank tensor, times Qj, which is my the cause vector, right. So I am causing, this is the cause, this is the effect, and the tensor Tij relates the two. Okay. And the tensor is a second rank tensor because I have two indices, right. Now in this case, so let us ask the question, right. So if I do a coordinate transformation, which means so I will do a coordinate transformation. I know how to transform vectors, right. So if I have a vector x1, x2, x3, and I do a coordinate transformation into, and then this vector will, so let us say I have a Cartesian coordinate system, this is x1, this is x2, and x3 is coming out of board, right. I sort of rotate this, right, so with certain angle, right. Then I get a new vector, right. So in the new system, so and then I am actually looking at so one of these vectors. So this is the vector of interest whose coordinates are x1, x2, x3, right. So this is, let us be a bit more careful in naming these things. So I am going to name the axis sorry, there is some. So I am going to name the axis as axis 1, axis 2, axis 3. Okay. So and then I have a vector which is x1, x2, x3. Now I am going to transform this into axes which are 1 prime, 2 prime, 3 prime, right. So by rotating or by doing some sort of an operation, right. So or by inverting certain things, right. These operations are going to be very important very soon. So I am going to transform this into 1 prime, 2 prime, and so I can also choose to rotate about the third direction, so and then 3 prime, right. So then x1, x2, x3, right, so which is my this vector in the new coordinate system has different names, right. So it has to be addressed differently, right, and that addressing is x1 prime, x2 prime, x3 prime, or in other words we say x1, x2, x3 transforms into x1 prime, x2 prime, x3 prime, right. Now how do you deal with such transformations? If it is transformations such as there are 3 transformations that I will write, but I will not really describe everything today because there is going to be time in the next classes when I am actually going to talk about all these transformations. So one is what is called rotations. So rotation of a coordinate system into another coordinate system. One is what is called roto inversion. Do not ask me what this is right now, I will tell you what this is in a later class, and the other operation is what is called inversion, right. So we can transform one coordinate system into another coordinate system, and this transformation can be through rotations, what are called roto inversions, and inversion operations. So we will actually look at more details. All these things can be described as so all these transformations can be described as simple matrices. These matrices are different from tensors. So although these are also so I am just going to write them as Aij with 2 indices.
so for example, rotations can be just described as a matrix consisting of direction cosines, as you may know already, right, and so on and so forth. But these are all all these operations can be described as matrices, right. So, in some sense, if I am transforming from x1 prime, I am transforming to x1 prime, x2 prime, x3 prime. This is the new coordinate system from an old coordinate system which is x1, x2, x3, right. So, what I will do is I will use a matrix, I will use a so the transformation happens if I just multiply all this the vector in the old coordinate system which is x1, x2, x3 with this matrix, right. So, this matrix is A11, A12, A13, A21, A22, A23 and A31, A32, A33, right. So, if I call this matrix as A, so x dash equal to A times x, right. So, this is a simple matrix multiplication which physically tells me how a coordinate system is transformed, how a vector in a coordinate system gets its new indices in the new coordinate system. Okay. So, that is one way of interpreting it. Alright. So, all these things are matrices, and these matrices, so especially if I am doing these operations which is rotation, roto inversion and inversion, these matrices have a certain property, and this property is that so if matrix is A inverse is the same as A transpose, or these are what are called orthogonal matrices, right. So, in other words, if I look at x I dash, right. So, these are the new coordinates. In terms of the old coordinates, it is Aij xj, right. But since the inverse is the same as transposing it, right, if I do an inverse operation, which means I go from xj dash, I go from new coordinates back into old coordinates and then get to xi, all I need to do is I need to use a matrix element which is Aji, right. Because the inverse, I am supposed to use an inverse, so an element in the inverse of A, which is A dash ij or something like that, but that is exactly the same as just transposing this matrix, right. So, if I transpose it, I get Aji, right. So, the orthogonality ensures that this is indeed the case. Okay. So, this is how you transform from new to old vector to new vector, new indices of the same vector, right. So, in new coordinate system, and this is how you transform from new indices in the new coordinate system to the older indices in the older coordinate system. Okay. So, these are the two expressions. Now, based on this, right, so I am going to next ask a question: how does a tensor, a second rank tensor transform, right. So, upon a coordinate transformation, right. Now, I have a second rank tensor which is Tij, right. Tij relates a vector Pi, right. It is relating two different vectors here, right. So, Pi is polarization, Qi is electric field, something like that, right. Whereas, the matrix is just changing the coordinate system from one, it is the same vector essentially, right. So, how do I see this vector in a different coordinate system? Okay. So, physically these are different ideas, although in second rank, when I am denoting second rank tensors and second rank matrices, it tends to get a bit confusing. Okay. So, if I have Pi equal to Tij Qj, right. So, the question now, I will write it in this color, is how does Tij transform with coordinate transformation? So, in other words, I am going to coordinate transform so let us say I have P dash, P gets transformed into P dash, right. Q gets transformed to Q dash, right. So, if this is the case, what happens to Tij? How does that get transformed? Okay. So, let us for that, so let us write P dash in terms of P, and so let us follow this chain, right. So, it becomes easy to derive, and then P in terms of Q and Q in terms of Q dash, right. So, this means in terms of, right. So, this means in terms of, okay. So, now what is P dash in terms of P? So, P dash is nothing but a transformed vector of P. P is the old vector, P dash is the new vector. So, P dash of let us say I equal to A I, for a reason I am going to use a different index, I am going to use A I k P k, right. So, A is the transformation matrix, P k is the old vector in the older coordinate system, and P I dash is the vector in the new coordinate system. Okay. Okay. Now, what is P k itself in terms of Q? Now, P and Q are different, one is a cause, one is an effect, right. These are different quantities, right. So, P k, but they are related, different quantities are related by a material property, that is your tensor, right. So, P k will be T from this equation here, T times K L, T K L times Q L, right. And then Q L is in the old coordinate system, you can look back here. So, how do I get old coordinate system from the new coordinate system? I just transpose the Aij vector, right. So, I am eventually going to make this Qj dash, because I need a Ti dash T dash Ij, right. So, I will have A, J and L, right. So, that is how it transforms, right. So, Xi is Aji Xj dash. So, QL is AJL QJ dash. Okay. So, then I will combine all these three, and from all these three equations I get Pi dash equal to Aik AJL, right, TKL times Qj dash, right. Whereas, so Pi dash is also my new transformation vector, which is T dash Ij Qj dash, right. So, in that sense, so if I am looking at this equation and this equation, it just means that Tij dash is nothing but Aik Ajl Tkl, right. In other words, if I go up, okay, so I go down, my tensor T, this is the tensor, that this is a transformed tensor, right. So, now what is the new tensor, new property that I am seeing in this new coordinate system, right. So, I am measuring with respect to, I am measuring the property with respect to a newer coordinate system, right. So, I will measure a different property, but I mean it's not because the property itself has changed, it is because my coordinate system has changed, right. So, how does it transform? It transforms simply as so how do I, it is Aik Aiajl times Tkl, right. So, Tkl is the older tensor transforms to a newer tensor, and the indices, so one index belongs to the older tensor, the later index belongs to the older tensor, and the former index of this matrix belongs to the newer tensor. Okay. So, this is how tensors of second rank transform. In other words, if I give you a quantity, right. So, I do not tell you that it is a tensor to start with, all this while I have been hinting you, I have been naming this T, meaning so there is some unsaid thing that T should be a tensor eventually, right, and so on and so forth. I have been hinting you that this should be a tensor, but if I do not tell you anything, right. So, if I give you a quantity and I tell you that this quantity transforms using this law, right. So, this is the transformation law for this quantity, right. Then I reverse what I am just saying, and I say that this quantity, the quantity, any quantity, so I will write this as equation whatever x, because I am not actually counting the equation. So, let me just write it as any quantity that transforms according to equation x is defined by definition, right. So, I am going to define a tensor like this now as a second rank tensor, right. So, this is now my definition of a second rank tensor, right. Now, okay. So, I can also do the inverse that I would like you to prove, right. So, how this is newer coordinates, this is tensor in the older coordinates, right. So, if I do the inverse, right. So, if I come from if I go to old coordinates, if I go back to old coordinates from newer coordinates t dash k l, right, again it is the same law that says, you know, so this is now k I a L J, right. So, I mean again it is the same thing because of the A inverse being equal to A transpose, this sort of a thing works, right. So, this is going from new to old, this is going from old to new, right. So, if you know, so if any tensor transforms using these equations, you call that if any quantity transforms using these equations, you call that a tensor, right. So, you call that a second rank tensor. So, I am flipping back this mathematics and I am actually defining this as a tensor. Okay. I can extend this, I do not need just I mean, so it is if I have a tensor of 3 indices, right. So, T I J K, right. So, I can call this a third rank tensor if it transforms as per this law, right. So, T dash I j k is equal to T I L T A sorry A I L A J M A K N times T L M N. So, this is in the old coordinates, this is in the new coordinates, there is a transformation matrix given by A and a third rank tensor transforms using this law, using this equation. This is the definition of a third rank tensor. In other words, you know, so any quantity I will probably I will rewrite it, any quantity that transforms as above is a third rank tensor. Okay. Then I mean, so first rank becomes much easier. So, T I equal to just A I j T j dash, that is just your pyroelectric tensor, this is a first rank tensor. Sorry, I must do this, there is no dash here. Sorry. Okay. Or you know, so I can write so this is new old to new, but I can also do new to old, right. So, T j dash A j I, right. So, this is how a first rank tensor will transform, right. So, anything that transforms using these transformation laws, any quantity that transforms using these transformation laws, equation x1, equation x2, equation x3, equation x4, right. So, these are what are in general called tensors, right. So, that is the definition of tensor of different ranks, right. So, is any quantity, again I am rewriting, that is okay, right. So, this is to impress upon that this is the definition of a tensor that transforms as per equations x1 to x4, right. So, this quantity will be called a tensorial quantity, or this is a tensor of a certain rank, right. So, rank is dependent on how many indices this tensor carry. Okay. Okay. So, that takes us to the next point, which is what is, you know, so okay, so second rank tensors, I understand which properties are second rank tensors, conductivity, susceptibility, right. So, all these are second rank tensors. Now, what about third rank tensors? Do we know of any properties that are third rank tensors? Indeed, you know, so that is, you know, so if I have stress, right. Now, stress, as I will, you know, describe in the next class, is actually a second rank tensor. Stress by itself is a second rank tensor, it is not a property, but it is a tensor, right. So, it is what is called a field tensor. You know, so how is stress defined? Stress is nothing but sigma I j is f I by A j, right. So, A is, you know, area vector in the j direction. So, there should be some force acting in a certain direction and that force should act on a certain area, right. So, that gives me the stress tensor. Okay. So, sorry, so I will not use sigma because sigma is for conductivity, I would rather use x for stress, right. Now, stress is a second rank tensor. Now, if I apply stress and I create a charge, right. So, I said I can create some polarization in the material by applying stress. I apply stress in KL and I generate polarization in the I direction, then what what is the material property that relates the stress applied to the polarization generated? This is a cross coupled property, this is an electromechanical property, and we said that this is nothing but d I, okay, so I j k makes sense. So, my stress will have indices of j k, okay. So, d I j k, right. This is a third rank tensor, right. So, d I j k is a third rank tensor, stress is a second rank tensor, polarization is a first rank tensor or a vector, and so d I j k, which is my piezoelectric coefficient, is a third rank tensor. Okay. So, we said pyroelectric coefficient is a first rank tensor or a vector, then we saw a bunch of second rank tensors, then piezoelectric coefficient is a third rank tensor. In the next class I will look at some optical properties, right. So, I have so far not looked at any optics, although the course says that there is optical properties that are third rank tensors, right, some nonlinear properties. Okay. So, for completion, right. So, let us also look at what are these properties that are so third rank is piezoelectric tensor, that is one of the properties. What about fourth rank tensors? Which is a property of the material, right. So, I said all material properties can be described in as tensors, right. So, what is a fourth rank tensor? A fourth rank tensor has 4 coordinates t, I, j, k, l, that is a fourth rank tensor, right, and the number of elements in this fourth rank tensor become too many to handle, right. So, we at the maximum do up to fourth rank tensors in this course, and if there are other tensors, well, okay. You know the framework to deal with them, right. So, now what is a good fourth rank tensor that is used in material science? These are the so called so if I apply stress in KL direction and I generate strain in IK direction, what relates stress and strain? Strain is also a tensor, by the way, this is strain tensor. So, we will actually look at stresses and strains separately in the next class, that deserves a class by itself, and XKL is the stress tensor. Both these are second rank tensors, this is second rank, this is also second rank, okay. And the quantity that relates these two, stress to strain, right. So, I apply stress and I generate strain, is what is called compliance, right. So, now compliance, I said, is mechanical engineers want to use the letter S to denote compliance. This is compliance, right, denoted by S. So, this is SIJKL. Now, SIJKL is a material property or a response function which is a fourth rank tensor. So, that is why mechanical engineers want to deal with very simple materials which are isotropic in nature. So, that these sort of monstrosities become simple to handle, right. But there are materials which are monstrous, and then we have to understand how to handle them, okay. So, similarly, if stress is the effect, so Xij, and strain is the cause Xijkl, okay, Xkl, then the tensor that relates these two is what is called a compliance tensor. I will write it as C, assuming that you do not confuse it with CPs and CVs. This is compliance tensor, but it is a tensor, right. So, Cijk, sorry, this is stiffness tensor. See, it gets a bit confusing because this is S is the compliance and C is the stiffness. C is like your Young's modulus, right. So, if I do a tensile stress experiment, a tensile testing experiment, I just pull the material right in one direction, and then so in the elastic region, the strain that I apply the tensile strain x11 let us say, is related to the tensile stress through what is called the Young's modulus. So, this is nothing but the Young's modulus. Okay. So, with that, so let me summarize, and we will stop with tensor algebra there. So, tensor algebra, the little bit of tensor algebra we did was just to say that this is a tensor, right. So, what is a tensor? A tensor is something that transforms according to the transformation laws. Any quantity that transforms according to the transformation laws that we derived is called a tensor. All the properties that we are going to talk about are tensors. They can be different in different directions. These are called anisotropic properties or anisotropic materials in some sense, right. They do not need to be isotropic. Okay. So, as a result we delved a bit into this tensor algebra, but then we said that so that there are properties which are different rank tensors. The complexity of the property, the structure, the mathematical structure of this property is simplest for a scalar Cp, for example, but I look at another property that is also denoted as a C, that is a stiffness, that is a 4th rank tensor. I need some 3 times 3 times 3 times 3 if I am not so to a first order of approximation, although the number of quantities will reduce, right, but I have 4 indices. So, essentially I need 3 power 4 such quantities to describe my complete stiffness tensor, right. Then I have 3rd rank tensors. Piezoelectric coefficient is a 3rd rank tensor, right. This is cross coupling, right. In the next class I will look at some nonlinear properties which are also 3rd rank tensors and 4th rank tensors, right. And then there are 2nd rank tensors. Okay. Now, where we are going with this in the next few classes, where we are going with this, okay, so there are all these properties. Now, we understand that properties are tensors of different orders. Where we go with this is there can be seemingly unrelated properties of the same rank, right, a 3rd rank tensor. Piezoelectricity is a 3rd rank tensor. In the next class I am going to talk to you about what is called 2nd harmonic generation tensor, that is also a 3rd rank tensor, right. They are seemingly unrelated, okay, but a material structure and symmetry relates them. If I say that in a material there is no piezoelectric coefficient, there is no 2nd harmonic generation, right. They are completely unrelated. One is an optical property, one is an electromechanical property, right. So, on the face of it there is nothing can relate them, but there is this beauty of symmetry, right, in the material. There is some symmetry element in the material that is going to tell me that 3rd rank tensor is 0, this 3rd rank tensor is also 0. It unites all these tensors of the same rank, right. In that 2nd rank tensor, sigma 1 2 should be 0. So, chi 1 2, which is a capacity, which is a susceptibility, that also should be 0, right. So, material symmetry tells me so relates different properties, right. So, different seemingly unrelated properties as long as they have the same rank of tensor. Okay. So, we are going towards that, we are setting up stage towards that, maybe that will happen in the next 2 classes, but in the next class we will again start with some nonlinear properties and relax this assumption of linearity and then see what is the tensorial notation of that. Okay. All right. So, see you in the next class. Thank you very much.